Okay, so let's start with these papers then. First of all, we have paper 5 variant 2 from the session November 2023. Now, let me have a look at the questions that you have asked on the WhatsApp group. Look at the polls to see which questions you want me to do from this. Okay, so these were the two papers that I asked you about. So from paper 5.2, that's this one, November 2023 paper 5.2, you want me to do questions 5, 6, and 7. These are the questions that have the most number of votes. We will do these 3 questions. And then from 5.3, we will be doing questions 5 and 6. Sorry, 5 and 6. And then if we have time, probably 1 as well then, okay? Yeah, so 5 or 6 questions. These are what we plan to do in this particular session. Now, again, just a reminder, if you want to send me a message, please send that to this account. Let me just change the name of this account here. Send your messages to this account that says message here. This is where you should be sending your messages. Okay, and if you have any questions at any point, raise your hand or write in the chat box. Otherwise, I'm just going to keep moving on, assuming that you understand what we are doing. Okay, so in the polls, I see questions 5, 6, and 7. These are the questions that most of you had problems in. Let's start with those questions. So remember, today we're doing difficult questions from these two papers. Okay, November 2023, paper 5.2 and paper 5.3. Okay, so let's start with question number 5, first of all. Okay, question number 5 from this. It says the heights of the members of a club are normally distributed with mean 166 centimeters and standard deviation 10 centimeters. We have the mean and the standard deviation. We need to find the probability that a randomly chosen member of the club has height less than 170 meters. Now, it's a normal distribution question. They've told you the mean of the distribution. The mean of the distribution is 166, and the standard deviation of the distribution is 10. We need to find the probability that a randomly chosen member of the group has height less than 1 centimeter, so 170 meters. Assuming that we represent height by x, what we're looking for is the probability of x being less than 170. Now, this is a simple, normal calculation. You have the mean given, you've got standard deviation given, you have all the data given, you need to find the probability. How do you do that? You first convert it to z, so it can be written as probability of z less than, using the formula, z equals x minus mu over sigma. You convert it to z first of all, so it becomes 170 minus mu, which is 166, divided by standard deviation, that's 10. And that gives you probability of z less than 4 over 10, which is 0.4. Now, is this the standard form? Yes, it is the standard form, z less than a positive number. That means you can look at the formula sheet and find out the result of this directly from the table now, right? We don't have to convert it to any other form. This is the form that we need generally to use the table, z less than a positive number. It is that form. Let's go to the table and find the probability corresponding to this z value. This is the formula sheet in which you've got this normal distribution table. What's the z value that we have corresponding? What's the probability that we have corresponding to z value of 0.4? It's 0.6554. And that's what we write here. We say the probability is 0.6554. And that's what we were looking for. Okay, that's the first part, pretty straightforward. Let's move on to the next one. Now it says, given that 40% of the members have heights greater than h centimeters, find the value of h correct to 2 decimal places. Okay, Given that 40% of the members have heights greater than h. 40%, what does that mean? What's the probability of someone having a height greater than h? The probability of someone having a height greater than h, that is 0.4, right? 40% in decimals, that's 0.4. We need to find the value of h, corrected root decimal places. Now this is inverse normal. We've got the probability given and we need to find some missing information in the data. Now, how do you do this? You first write it in terms of z. You say probability of z greater than, so corresponding z notation would look like this: z greater than some value that is equal to 0.4. Okay. If the x value is h, we need to find first the corresponding z value for h, because then after that we can use the formula z equals x minus mu or sigma to find the unknown that we have here. But what's the z value corresponding to this h value? That's what we need to figure out. However, for that, the condition is we want to convert it to this form first of all, z less than a positive number, because in order to use the table, this probability function, this probability expression should be in this form. Now, we have to convert it to this form first of all. Okay, how do you do that? First of all, you figure out whether the z value is positive or negative, right? Because we need a positive value. If it's negative, we'll have to convert it to positive somehow. Is it positive or negative? How do you figure that out? Think of the normal distribution curve. This is what the normal distribution curve looks like. You've got z in the middle. Zero in the middle. It's a z distribution. Zero. The area to the right of this z value, this greater than means you're looking at the right of some value. Area to the right of some z value is 0.4. Now, is 0.4 larger than 0.5 or smaller than 0.5? 0.4 is smaller than half of the area, half of 0.5, right? It's smaller than 0.5. So what that means is z should be placed in such a way that to the right of it, the area is smaller. If we were to place z here, what's the area to the right? The area to the right is bigger, it's larger. So z can't be here. If we place z here, then the area to the right is smaller. So that means z is going to be on the positive side. Z is going to be on the positive side. So the z value here is actually positive. That's the first thing you have to do. You have to figure out whether z is positive or negative. And we figured out here z is positive. And what we know now is this region. How much is this region? This is 40%. That means 0.4, right? This area is 0.4. Now, this is not the standard notation for using the table, because we have area to the right of it. However, if the area to the right of the z value is 0.4, what about the area to the left of the z value? 1 minus 0.4, that will be 0.6. So this remaining area to the left, that is 0.6. So what you can do is, you can write this like this. You can say z less than that positive value of z is actually 0.6. So considering this positive z value, the area to the left of this is 0.6. If the area to the right is 0.4, the area to the left is going to be 0.6. Now it's the standard form. We can go to the table now, find the z value corresponding to a probability of 0.6. Let's go to the table. Probability is 0.6. Find the z value corresponding to that. Okay, so probability is 0.6. Where do we have 0.6 in probability? Remember, we have to look at this region here. Z is on the sides here, the first row and the first column, and the probability values are in the middle of the table. 0.6, where is 0.6? We don't have exact 0.6 here, so we take the smaller value. It's visible here, right? Yeah. It's the smaller value, 0.5987. What's the corresponding decimal places that we have for z here? 0.2 and 5. So we get z equal to 0.25. These are the first two decimals. Now, what about the third decimal? We wanted 0.6. That means 0.6000 to 4 decimal places, right? What we found in the table was 0.5987. How much do we still need to add to 0.5987? What's the difference between these two values? 13 at the end, right? So we need to add 13 to it. Let's go to the right. Where is 13? 13 is going to be between 12 and 15. It's closer to 12 as compared to 15. So we use 12. What's the corresponding third decimal place here? That's 3. So the z value that we get from the table is 0.253. And that's what we're going to use here. We say the z value is 0.253. Now, if the actual z value was negative, we would put negative here, but we know that the z value was positive, so we just use that same value. And now we put this in the formula, z equals x minus mu over sigma. What's the value of z? 0.253. That equals x. In place of x, we put h minus the mean. Mean was 166. And the standard deviation was 10. And that's going to give you the value for h. And you can see what that turns out to be. 0.253 into 10 plus 166. And that's giving me 168.53. Okay, I think it's 168.53. That's what I'm getting. It's not 0.3, it's 53. 168.53. That's the value of h that we have. Yeah. Okay, that was the second part. Again, not that complicated. Let's look at the third part now. The third part says the random variable x is normally distributed with mean mu and standard deviation sigma. So we have both of those things missing. Okay, let me just answer that question. Also do 1 minus z 0.4. I'm not sure what you mean by this, Sufyan. 1 minus z of 0.4. What does that mean? So we had 0.4 here. We subtracted 0.4 from 1 to get 0.6. Oh, you're saying we in the table we find so there's a question that says somebody asking, can we take the value corresponding to 0.4 from the table for z and then subtract it from total probability? 0.4 is the probability. We are finding the corresponding z value. It would not make sense what you're saying. How do you subtract this z value from 1? It's the probability that's 1. You can't subtract a z value from 1. That would not make sense. That would be correct what you're saying. From the table, this is the value that you have to read, 0.6. You can't read the value at 0.4. That's not going to give you anything useful. Okay. All right. Now, the random variable x is normally distributed with mean mu and standard deviation sigma. Given that sigma equals 2 over 3 mu, find the probability that a randomly chosen value of x is positive. Now, what does that mean? Randomly chosen value of x is positive. So we need to find the probability that x is greater than 0. This is what we want to find out, right? Positive means it's greater than 0. Okay. Now, is this a different variable? Yeah, it's a different variable. Mean of this distribution is mu and standard deviation sigma. How do you find this probability now? X greater than 0. Let's try this. Now, is this simple normal distribution or inverse normal distribution? This is simple normal distribution, right? We convert it to z first of all. It's x greater than 0. Let's convert it to z. What's going to be the corresponding form in terms of z? Z greater than 0 minus mu over sigma. Right? That's what it becomes. All right. Now we have probability of Z greater than minus mu over sigma. Now both of them are unknown. However, they have given that sigma equals 2 over 3 times mu. So in place of sigma, what we can do is we can input 2 over 3 times mu. And what happens if we do that? Mu and mu get cancelled, and we are left with probability of Z greater than minus 1 over 2 over 3. That becomes minus 3 over 2. And that's probability of Z greater than minus 1.5. Okay, that's what we get. Now we can find this from the table, but for finding the probability from the table, we need this form, Z less than a positive value. So we need to convert it to that form first and then find the corresponding probability from the table. How do you convert it to this form? Let's think of the normal distribution curve and think of how it looks like. This is what the normal distribution curve looks like. We have 0 in the middle for the Z distribution. Minus 1.5, where is minus 1.5 going to be? It's going to be on the left side. We want the area to the right of minus 1.5. So basically, we're looking for all of this region. This is what we want to find out. But the table does not give us these areas. The table only gives us areas to the left of some positive value. So how do we convert it to that standard form that we can use the table for? We can flip this. We can say probability of Z greater than minus 1.5 is the same as the probability of Z less than 1.5. So this area to the left of 1.5 is going to be the same as that because the curve is symmetric. So we can just flip this, right? We can flip the curve to get probability of Z less than 1.5. We can say this area is the same as this area. And now this is the form that we can use the table for. Find the probability for the Z value of 1.5 and see what that is. At 1.5, we have 0.9332. So this probability turns out to be 0.9332. And that is what we were looking for. Okay. When do we know how do we know when to flip? Well, you have to remember all of those cases, not actually memorize, but understand the logic of all of those cases in normal distribution. So your table can only give you Z values to the left of a positive number. And then if there's any other form, you need to understand all of these different cases, right? The standard form is this one. Where is that? Yeah, this is the standard form, Z less than a positive number. But if you have any other form, you need to be able to convert it to that other form. For example, if it's Z greater than something, you have to do 1 minus that. If it's Z greater than a negative value, you have to flip that. If Z less than a negative value, again, you flip that and do 1 minus that thing. You have to understand all of these cases, how to find probability when Z is between two values, between two positive values, when it's between two negative values, between one negative value and one positive value. You need to understand all of these cases. Generally, we have to flip when the value here is negative. When it's negative, we have to flip first. Okay, and then look at how to convert it to this standard form. So generally, when it's a negative Z value there, we have to flip first to make it positive and then convert it to a less than sign somehow. All right, so that's the probability that we're getting. That was, I think, not very difficult, this question. This was, I think, one of the average difficulty level questions on normal distributions. On normal distribution, you would definitely find more difficult questions in this as well. But let's look at the next one now. Question number 6. Okay, now it says Freddy has 2 bags of marbles. Bag X contains 7 red marbles and 3 blue marbles. Bag Y contains 4 red marbles and 1 blue marble. Freddy chooses one of the bags at random. A marble is removed at random from that bag and not replaced. That means you're not putting that marble back in the bag. Okay. A new red marble is now added to each bag. A second marble is then removed at random from the same bag that the first marble had been removed from. Draw a tree diagram to represent this information, showing the probability on each of the branches. Now, that's a fairly complicated looking scenario. So let's break it down. So go in sequence. When you're drawing a tree diagram, do things sequentially. Do them step by step. What's the first thing that's happening? The first thing that's happening is she's choosing one of the bags at random. Okay, one of the bags is being chosen at random. Now, if it's being chosen at random, that means the probability of choosing X or Y, that's basically equal. So you have two possibilities. First of all, you could either choose X or Y. They have equal probabilities. So this is 0.5 and this is 0.5. Because they're choosing randomly. A marble is removed at random from that bag. So whichever bag is chosen, one marble is removed from that bag and not replaced. Okay, so if it's the first bag X, what are the two possibilities? When a marble is taken at random, what could those two colors be? It could either be red or it could be blue. What's the probability of having a red marble? 7 over 10. The total number is 10. 7 out of 10. That's 0.7. And for blue marble, it will be 0.3. And in case it was a yellow marble, in case it was the bag Y first, you could have a red marble or a blue marble. The probability of red marble is 4 out of 5. That's 0.8. And the probability of having a blue marble is 0.2. This happens in the second step. So this was the second step that we looked at. A marble is removed from the bag and not replaced. What's happening next after this? The next thing that's happening is a new red marble is now added to each bag. Okay, so now they're adding a red marble to each bag. There's no probability involved here, so we're not going to have any branch for this. It's just that initially we had 7 red marbles and 3 blue marbles and 4 red marbles and 1 blue marble in each of those two in both of those bags. Now, after this first step, one new red is added. Then what happens? A second marble, after red marble is chosen, a second marble is then removed at random from the same bag that the first marble had been removed from. Okay, so if the first marble was removed from bag X, now you remove a second marble from bag X again. There are two possibilities here. Similarly, if the first marble was removed from bag Y, again, you have two possibilities here. You've got two possibilities here. For the second time you choose a marble, again, you've got two possibilities for each of these cases. You could either have a red marble or a blue marble, red marble or a blue marble, red, blue, red, blue. Now, keep in mind the number of marbles that we had in the beginning and what's happening at this particular point. Now, in fact, it might make it easier to figure out what's happening in the next step if you write these values as fractions instead, so that you know the actual number as well. So red marbles were 7 initially, so we can write them as 7 over 10, and this was 3 out of 10. So total balls were 10, 7 were red, 3 were blue. Okay, so writing this as fraction would make it easier to understand what to do in the next step. This is 4 over 5, because we had 4 out of 5 red marbles, and then here it was 1 over 5. Now think about it. If the first time marble R was taken from box X. How many marbles are we left? How many red marbles are we left with at this point? 6, 3. 6 red and 3 blue. However, a red marble is added here. So it becomes 6 plus 1. So what's the probability of getting a red marble again? It's again going to be 7 over 10. And what's the probability of having a blue marble again? That is again going to be 3 out of 10 because the total number becomes the same as before once a red marble is added because you removed one red and they placed one red back inside. This is what you get in the first two branches. If, however, from bag X the first time, a blue marble was taken. The first time the blue marble was taken, what's the number of red marbles and blue marbles at this point? 7 red and 2 blue after a blue is taken out. And then a new red marble is added. So the number of red marbles becomes 8 now. So the second time, the probability of getting a red marble is 8 over 10. The probability of getting a blue marble is 2 out of 10. That's what you get in this case. Okay. Let's move on. See what happens in box Y now. When you take a red marble the first time, what's the number of marbles for each of them? How many red do we have? How many blue do we have? After taking one red out, we had 4 initially. Now we're left with 3 red and 1 blue. And you add 1 red again. So that's 3 plus 1, 4. So probability of having a red marble again is still 4 over 5. And this is 1 over 5. In the other case, however, when a blue marble was taken the first time, how many red marbles do you have? How many blue marbles do you have at this point? You had 4 left of red marbles and 0 blue marbles. You add 1 more, it becomes 4 plus 1. 5 over 5, the probability of having a red marble the second time is basically 1 because there are only red marbles in the box now. There's no blue marble. The probability of having a blue marble is 0. So this basically means you can write it like this if you want, 5 over 5 and 0 over 5. Right, so that's 1 and 0. This is what the tree diagram looks like. Okay. Now let's move on. That was part A. I hope that makes sense, right? Any problems? Now it says, find the probability that both of the marbles removed from the bag are the same color. Okay, now that you've made that tree diagram, I think the rest of it is not going to be very difficult now because the rest is going to be a standard probability question. It says, find the probability that both of the marbles removed from the bag are the same color. Now, what are the possibilities that we have? It could either be red, red, blue, blue, red, red, blue, blue. You just add all of these probabilities, and that's going to give you the result. Now, what's the first case that you choose bag X, pick up a red marble the first time, pick up another red marble the first time. Let's see what that gives us. It's going to be 0.5 into 7 over 10 into 7 over 10. That's the first case. Okay. That's basically this case. This. That you choose X, box X, and you choose 2 red marbles from that. And then the next possibility is you select box X, and from that box X, you choose 1 blue marble and the second blue marble. Laiba, let me come back to your question in a moment. So if we have both blue marbles taken out, what does that give us? That's 0.5 into 3 over 10 into 2 over 10. That's another possibility of getting same colored marbles. Then if you chose box Y, you could get red from that. What does this give you? 0.5 into 4 over 5 into 4 over 5. And then finally, from box 5, you could choose B and B as well. What does that give you? That's going to become 0 because you have a 0 in there. 0.5 into 1 over 5 into 0. And now you just evaluate all of these cases and add them up together. That is going to give you the final result. You can see what this turns out to be. 7 over 10 into 7 over 10. What's that? Into 0.5, in fact. 0.5 into 0.7 into 0.7. The first one is 0.245. I recommend you evaluate each one of them separately as well, but because often there is a condition probability part later. Yeah, so write down each of those probabilities separately. They will help you in the next parts. Okay, what's the first one? The first one is turning out to be 0.24. Okay, then 0.5 into 0.3 into 0.2, that's 0.03. 0.5 into 0.8 into 0.8, that's 0.32, and this is 0. You just add all of these cases, and that gives you the result. Okay, because it could be any one of those 3 cases. So basically, now add those cases, 0.245. You've done this calculation on the tree. You have shown that calculation on the tree, or you can either show this calculation here, or in this space, you have to show calculation somewhere so that the examiner can check your working. It's a 4-mark question. You should not write the answer directly. You need to show this working somewhere, that you're multiplying this. Okay, this needs to be shown. 0.245 plus 0.03 plus 0.32, and that's going to give you the result. What do you get? 0.245 plus 0.35, and that's 0.595, right? That's 0.595. That's what we're getting from this. 0.595. That's the probability that both of the marbles removed from the box are the same color. Okay. No, so the question is, can we show the working above the question? That means you can show the working here. If you're showing the working above, you should show that along with the tree. But if you have to write it separately, then it's better to write in the space that's given here. You can either show your working along with the tree, and that's okay. But if not with the tree, then you should write here. Don't write in this space. Okay. All right, so that's 0.595. Now it says, find the probability that bag Y is chosen given that the marbles removed are not both the same color. Okay, now what does that mean? Probability that bag Y is chosen, probability that bag Y is chosen, given that both marbles are not the same color. That's what you have to find out. Now, how do you do that? It's conditional probability. In the numerator, you would have the probability of both of these things happening together, probability of choosing Y and both not being the same color. That's what you're going to have in the numerator. And in the denominator, you have what is given. What's given? Not being the same color. Both not the same color. That's the probability that we're looking for. What about the denominator? Both not the same color. We have found the probability of both being the same color. That's 0.595. So what's the probability of both not being the same color? We just subtract this from 1, right? So the denominator is pretty straightforward to calculate, or you could do it directly as well. You could find this case, this case, this case, and this case, and add all of those 4 probabilities. And that will give you the same as this, as what you would get by subtracting this number from 1. So in the denominator, so this probability, both not being the same color, this is basically 1 minus 0.595. The probability that you've calculated in the first part, subtract that from 1, and that will give you this probability. Now, what about the numerator? In the numerator, you want both of these things happening at the same time. That y should be chosen, and both of them should not be the same color. Now, when y is chosen, let's go back there here. When is y chosen? Here. When are both not the same color? It's either this case that you choose y and you have first red and then second blue. That's one possibility. Or you choose y and you have first blue and second red. These are the two cases that you're going to have in the numerator there. What are these two cases? Let's evaluate them. 0.5 into 4/5 into 1/5. And the second one is 0.5 into 1/5 into 5/5. These are the two cases where both of those things are happening together, that you are choosing y and both are not the same color. 0.5 into 0.8 into 0.1, 0.2. That's giving me 0.08. 0.5 into 0.2 into 1, that is 0.1. These two cases together are going to be in the numerator here. So in the numerator, we have 0.08 plus 0.1, right? That's the case that we get here, 0.08 and 0.1. Let's evaluate this. What do we get? 1.08 divided by 0.405. And that's giving me something that's wrong. Let me check this again. Okay, sorry, I wrote the wrong value there. 0.1 plus 0.08, that's 0.18. 0.18 divided by 0.405, that is giving me 4/9. Right, I was getting something greater than 1 earlier. This is 4/9, and that's 0.444 in decimals. You can leave it like this. That's 4/5. That's what we were looking for. Okay. All right, now let me explain. That was the second part, yeah. Let me explain some of these questions that you're answering. You can respond to them. Okay, so one question is, second marble is removed, so won't we consider that in the tree diagram? Well, we are, okay, so Lai was asking, it says the second marble is also removed. Why are we not considering that? Well, we are considering that. This is the first marble that's removed. This is the second marble that's removed. So this step represents the first marble being removed. And this step represents the second marble being removed. So we are representing both of them here. We are not using X and Y again because they are saying the second marble is removed from the same bag that the first marble was removed from. So we don't need X and Y again there, because if the first marble was chosen from box X, from bag X, the second is also going to be chosen from bag X. So we don't need any other options for any additional option for X and Y again. This is just representing the first marble, this is representing the second marble. So we are considering that. Okay, I hope that makes sense. And now another question is from Divya. Why can't we multiply probability of Y and not the same color directly? Okay, so what you're saying is, in the numerator, we have the probability of Y and both not being the same color. Why can't we just multiply probability of Y with probability of both not being the same color? Now, that's a good question because I think a lot of people have this confusion. So you're thinking, since there's an and between them, just multiply the two, right? That's what you're saying. That since there's an and, we should just multiply those two probabilities individually like this. However, remember the conditions for independent events. Probability of A intersection B, that is equal to probability of A multiplied by probability of B. This is the condition for two events being independent. Probability of A and B, when you have to prove two events are independent, remember we used to use this. Probability of A and B, that equals probability of A into probability of B. This rule that we are talking about, it only is true for independent events. It's not a general rule that's always true. It's only for independent events. If these two were independent events, if Y and both not being the same color, if they were independent of each other, if they did not affect each other, then we could do this, yes. But if we are not sure about that, then we have to look at the diagram and see where both of those conditions are met. Both of those conditions are met in these cases. This is one case, and this is the second case, where you're choosing box Y, and when you're selecting a marble from box X, sorry, when you're selecting marbles from bag Y, and they're both different colors. So you have to look at the cases on the tree diagram, add up their probabilities. You can't just multiply like this. This rule only works when two events that you're talking about, they're independent events. Here, they're not independent. Is that okay? So in general as well, if you remember the condition probability formula, that's probability of A given B equals probability of A intersection B divided by probability of B. In general, probability of A intersection B is equal to probability of A given B multiplied by probability of B. This is the general rule. In general, A and B, that's equal to this into this, not probability of A into B. That's only in case of independent events. So we can't multiply them like this, like that. All right. Any other problems with this? Make sense? Okay, good. Let's move on to question number 7. Now it's a permutation combination question. It says, find the number of different arrangements of the 9 letters in this word. I'm not sure how to pronounce it, what it is, in which no consonant is next to another consonant. The letters D, M, N, and R are constants, and the letters A, E, and O are not consonants. Just a reminder, this is October, November 2023, paper 5-2. Those of you are asking, this is the paper that we're doing first. Next one is going to be 5-3 from the same session. Yes, Faizan, that's correct. That's correct. Okay. Find the number of different arrangements of the 9 letters in this word in which no consonant is next to another consonant. The letters D, M, N, and R consonants, and these are vowels. Okay, so the consonants do not have to be together. Let's highlight the consonants: N, D, R, M, D. Right? We have 5 consonants here, and 2 of them are repeated as well. There are 2 Ds. The consonants have to be separated. Now there are 5 of them. There are total 9 letters. So that means vowels and consonants, they are going to be occurring alternately because we have 9 in total, 5 consonants and 4 vowels. If the consonants all have to be separated, we start by placing the vowels. We make 4 places for vowels, 1, 2, 3, 4. We could use that dashes and stars representation, remember? So the objects that you have to separate, you use stars for them. And the objects that you do not have to separate, you use dashes for them. So you start by representing the objects that you do not have to separate. Vowels are what you do not have to separate. You represent them here. So what are the four vowels that we've got? A, O, E, A. Okay, so the vowels are A, O, E, A. Now they could switch their positions with each other. And between them are going to be consonants. There are 5 places for consonants. There are 5 consonants. We have these places for them. Okay. And here we could have those 5 consonants. They are D, M, N. There are 2 Ds. And M, N, and R. This is where we could have those consonants. These are the positions where the consonants should be. Now, in how many ways can we arrange these? What are the possible arrangements for consonants? How many consonants do we have? 5, and there are 5 places for the consonants. And how many ways can we arrange them? 5 factorial, right? However, 2 of them are identical. They are 2 Ds. So because of that, we divide by 2 factorial. And what about the vowels? We have A, O, E, A. They can switch places with each other, right? Vowels can switch places with each other. How many vowels do we have in total? 4. So that's 4 factorial. However, 2 of them are identical. There are 2 A's. We divide by 2 factorial because of that. And that's going to give us the result. What do we get from this? 720. Okay, thank you. That's the result, 720. That was the first part. That's what you do here. Why can't we use total arrangements minus the arrangements of consonants together? Well, we can't do that because the question says no consonant is next to each other. If you do total minus together here, what that does is, out of the total arrangements, it just eliminates the case where all consonants are together. However, what about the case when 4 are together, C1, C2, C3, C4, and 1 is separated? If you do this case would also be counted, but we don't want to count that. We want each consonant separated. So there should be no 2 consonants together. So for this, you can't use that method where you subtract the arrangements where these are together from the total. This method is not going to work here because here you have to separate all consonants. No 2 consonants can be together. So that method does not work here. Okay. All right. So it says find the number of different arrangements of the 9 letters in the word, the same word, in which there is an A at each end and the D's are not together. Okay. Now, how do we think about this? There are 9 letters again. We can think of this box's representation. Let's represent those 9 boxes. We don't have to separate anything here. We just have to have, in fact, we do have to separate these. Let's think about how we could figure this out. There's an A at each end. That means the first letter on the left is going to be an A. The last letter on the right is going to be an A. These 2 are A's. Okay. How many places do we have in the middle now? We have 7 places left in the middle. We have these 7 places. Now A's are fixed. They are not going to move. So there's nothing that you have to do about A's. They are fixed there. And they're identical, so it doesn't matter if this A is there or this A is there. It doesn't matter. We just fix those A's. So all we have to deal with is these 7 boxes in the middle. Okay. Now you could, here, since you don't only have 2 D's, you could use any of those 2 methods. You could do total minus together, or you could use the stars and dashes method. Both of them will work here. For 2 objects that need to be separated, both methods work. But for more than 2 objects, it depends which one of the two is going to work. Only one of those methods will work depending on what the context is. If we want all of them separated, in that case, we have to use dashes and stars method. Otherwise, we can use total minus together. Now, in this case, since we only have 2Ds, we could use any of the two methods. What we can do now is we can say, of these 7 letters in the middle, what's the total number of arrangements? What are the letters that we have in the middle? We've got N, D, R, O, M, E, D. These are the letters in the middle. How many total arrangements do we have for them? 7 factorial, but then there are 2Ds. We divide by 2 factorial because of that. That's the total number of arrangements without any restrictions. Subtract from that the case when you have the 2Ds together. What happens when 2Ds are together? We can put them in one box like this. And then in the remaining boxes, we've got the rest of the letters, which are N, R, O, M, E. How many boxes do we have now? 6 boxes. All of them are different. No 2 boxes are identical now. So we just do 6 factorial for that. So this is total minus the case where the 2Ds are together. You subtract that case from the total, and that's going to give you the result. You can see what this turns out to be. What's this number? $1,800. Okay, thank you. That's the result that we get, 1,800. Part B. Now let's look at the next one. It says 4 letters are selected at random from the 9 letters in this word. Find the probability that this selection contains at least 1D and exactly 1A. Okay, now this is a very important question, and it's been coming repeatedly in the last few sessions. Okay, so try to ask questions quicker than that, so that they're answered before we move on to the next part. So there's another question. Let me just answer that quickly and then move on to the next one. So they're saying, why aren't we going to divide by 2 factorial? Divide 6 factorial by 2 factorial because we have 2Ds? Well, no, because we are only considering these 6 boxes. This is counted as a single box. Okay, this is counted as a single box. We are not treating the 2Ds separately at all. So we don't have to divide by 2 factorial as well. Okay. Here we were doing 7 factorial. We were dealing with the 2Ds separately. So that's why we had to divide by 2 factorial there. But here, this is one single box. All right, so we don't have to do anything for that. Okay, now this is very important. You will see this question very similar. So questions very similar to this in the last few sessions, and they've come repeatedly. It says find the probability that this selection contains at least 1D and exactly 1A. Now, the complete explanation of why we're going to do what we're going to do is going to take quite long. So I'm going to direct you to something that you can use to understand this. And that is basically this particular video. I'll tell you the final result from this directly right now. Yeah. So look at that playlist that you have in the WhatsApp group. Look at that playlist and see this video. November. No, this is June. June 2021. Paper 5-2. Look at this video. Question number 6 in this. But I've explained why we are going to use the method that we're just going to use for questions like these. Okay? The whole reason for that. But for now, let me just tell you the result directly that you're going to remember. The logic of that you can find out in that video. But let me just tell you what you're actually going to do. Whenever you have probability, whenever you have to find probability, whenever you have to find probability of something, and you have combinations, which they're talking about selection, right? That means it's combination. And there is some repetition. You have repetitions in these letters. Some letters are repeated. When all of these things are there, what you're going to do is, to find the probability, you're going to treat all letters as different. Treat all letters as different. As opposed to if you were not looking for probability. If you were, for example, looking for number of possible selections, if you were looking for number of possible selections that contain at least one D and exactly one A, if you were doing something like that, you would just list down the outcomes like this. At least one D out of 4. Since you want at least one D, that means one D is already selected. And you want exactly one A, that means one A is already selected as well. You have 2 options left out of how many? What are the remaining letters that we've got? You have A, N, D, R, O, M, D, A. These were the total letters. Now it says exactly one A. That means one A selected. So you can't use another A now. This is basically eliminated. One D is already selected as well. How many letters are we left with? We're left with N, R, O, M, E, D. All of these are different letters. If they had asked you for the number of possible selections, if they had asked you for number of possible selections that contain at least one D and exactly one A, you would do something like this. You would say, you want 4 letters. One of them has to be D at least. Exactly one has to be A. That means there has to be one D, there has to be one A. Now, what are the remaining letters that you can still choose from? Since there is exactly one A, you can't choose another A. So we eliminate the A's. You still can choose the second D. So we still have that here. How many letters do we have here? 6. Out of those 6 letters you want to, you would do 6C2 for that, and that will give you 15. Okay. If you were looking for number of selections, this is all that you would have to do. Sometimes you have to make some other cases for this as well. And that's what you would do. This method works for number of selections with combinations and repetitions. However, when they're asking for probabilities, you cannot do it like this. And the reason for that is each of the possible outcomes that you have, for example, one possible outcome is DA, one possible selection is DA RO, for instance, another possible selection is DARD. These selections do not have the same probabilities because there are 2 Ds and the remaining letters are only 1. So because of Ds being repeated, probability of each of these 15 outcomes that you have, they're going to be different. And since the probabilities are different, you can't use that formula, number of favorable outcomes divided by total number of outcomes, in this case, when you have to find probability. Okay, now you'll find a more detailed explanation of this. I've given you some hint of why this is not working. In that video, I'll actually remind me in the group. I'll share that particular video in the group today as well. What you need to do instead here is, for number of selections, you would do it like this. And I think most of you who would have tried this question, I think for finding probability, you would have done it. You would have, when you attempted, you probably did it the same way as well. However, when you're looking for probability, this method is not going to work. Why? Because the probability of each of those cases is different. Okay. Awesome. I'll share that video. In that case, I've spent like 20-25 minutes explaining this in detail, why we're doing this. But you just need to remember this eventually. And that is, you have probability. you have combinations and repetitions. When you have these three things together, when you're looking for a probability and you're using combinations and there's some repetition, you are going to treat all letters as different. That's what you need to understand. And you would treat it like this. You would say, okay, which letters do we have here? We've got A's. How many A's do we have? Make separate cases for A's. So you have two A's and you have D's. There are two D's. And the remaining letters are not repeated. So make separate cases for repeated letters. We have two A's, 1 and 2. We have two D's. What are the remaining letters? N, R, O, M, E. None of them is repeated. We could consider them all together. The letters that are not repeated, let's call them X. The remaining letters, how many of them are there? 5. What are the possible cases that you have here now that satisfy the condition? So you want at least one D and exactly one A. At least one D and exactly one A. Let's consider all the possible cases now. There has to be one A, so A has to be 1 in all of those cases. Okay, what are the possibilities for D? You could have one D and then 2 remaining letters. You could have 2 Ds and 1 remaining letter. In fact, there's no other possibility that you get here. These are the only 2 cases that you are kind of getting here. Is that okay? 1A, 1D, 2 other letters, 1A, 2 Ds, and 1 remaining letter. There's no other case that you can think of. Now, in how many ways can you do this? For the first case, you are selecting 1 out of 2 A's, so that's 2C1. Remember, we are treating the letters as different. That's why we are saying 2C1. Otherwise, if the A's are identical, it does not matter which A we choose, right? We won't do 2C1 in general when we're looking for number of selections. But here, since we are treating all letters as different, we are saying one is A1 and the other is A2. We are selecting 1 out of those 2 A's. So it becomes 2C1. And then 1 out of the 2 D's, that's 2C1. And then 2 out of the remaining 5 letters, that's 5C2. And what about this now? 2C1 into 2C2 into 5C1. And that gives you the number of selections for each of these 2 cases that you have. What do you get from this? 2 into 2 into 10. 5C2 10. That's going to be 40. And the second case, 2 into 1 into 5. I think that's 10. And that's going to give you 50. These are the number of selections that satisfy the condition. And now, since you're looking for probability, what is probability going to be? Number of favorable outcomes divided by the total number of possible outcomes where you do not have any condition. What's the total number of possible outcomes without any condition? You have 9 letters. You have to select 4 out of them. That's 9C4. Again, we're treating all letters as different, so we can just do 9C4. Otherwise, if there's repetition, we can't use combination like that generally, right? But since we are treating all of them as different, the denominator is 9C4, and that's going to give you the result 50 over 9C4, and that gives you 25 over 63. And that's the probability that you've got. Now, this is something that you need to remember now. Whenever you're looking for probability and you have combinations and there are repetitions, this is the method that you're going to use. For number of selections, you would use the other method. We will see when that comes in maybe another paper, and then we can compare these 2 as well. And I'll share that video with you where I've actually compared the 2 possibilities. What happens when you have number of selections? What happens when you have probability? That's a concept that you actually need to know about. So that's why I'm not going to spend too much time on that right now, but I'll basically refer you to that recording. It's like 25-30 minutes. I will look at that. You'll understand the logic of why we're doing this. Okay. Why are we selecting from the remaining letters? Well, because we want 4 letters in total, right? So how do we make the total number of letters 4? If we are selecting 1A and 1D, we need 2 letters still. So we have to select 2 out of the remaining 5 letters, right? Okay, good. So that was this paper. All right. Let's move on to the next one quickly and look at the questions that you asked from that paper as well. So next we have paper 5.3. Okay, so from this paper, you asked about question number 5 and question number 6. Right, most of you had problems in these 2 questions. 5 and 6, let's have a look at them. So it appears from every paper you're having problems in permutations and combinations questions because they are normally the last couple of questions in papers. Yeah, so again, permutation questions here. And this is something else. Okay, all right. So this is now November 2023, paper 5, variant 3. Again, we're going to look at some difficult questions from this, and most of you have asked about questions 5 and 6. Let's do those 2 questions. Okay, let's start with this one. Question number 5. It says, probability that a driver passes an advanced driving test is 0.3 on any given attempt. Deepak keeps taking the test until he passes. Now, this is a keyword that you should actually remember. Until something happens, whenever it comes, mostly that's a geometric distribution. Remember, because in geometric distribution, we talk about number of trials, number of repetitions until you get your first success. So this word until is basically a keyword for geometric distribution. Now, you still have to see if all the conditions for geometric distribution are applying or not. But when you see the word until, that should remind you of geometric distribution. And then you have to think of whether the conditions are met or not. Now let's think about this. So it says the probability that a driver passes this test is 0.3 on any given attempt. Okay. Now, Deepak keeps taking the test until he passes. X denotes the number of attempts required for Deepak to pass the test. So that's clear. Number of attempts, number of trials needed until you get your success. Find the probability of X being between 2 and 6. Okay. What's the probability of success? It's a geometric distribution. We understand that, right? There are 2 possible outcomes. He could either pass the test or fail the test, right? 2 outcomes. Probabilities remain constant. Every time the probability of success is 0.3, probability of failure is 0.7. So the probabilities remain constant. And we're looking for number of attempts until first success. So that's geometric. Probability of X being between 2 and 6. One way to do this would be that you find all of these separate probabilities, and you can do that. It's not going to take that long. You can try that. X equals 2, X equals 3, plus X equals 4, plus X equals 5, plus X equals 6. You could find all of these probabilities and add them up together. That is one possibility. Okay, so what is this? What would this be? Q raised to power 1 into P plus Q square times P plus Q cube times P plus Q raised to power 4 times P plus Q raised to power 5 times P. And that should give you the result. That is one possibility. Okay. This is one possibility, but it's like 5 different calculations. You can do that and that will give you the result. Okay. You know P and you know Q. This would work in this case because there's only 6, right? But what if it was 2 to 20? That'll take too long, right? There's another way of doing this as well, and that's using that inequality formula that I told you about in the last session as well. For geometric distribution, we also have an inequality formula. Probability of x greater than r, that is q raised to power r. Right? That's the inequality formula that you can remember for, that you should remember for geometric distribution. Probability of x being greater than r is equal to q raised to power r. You have to convert this probability to this form somehow. Just like you do it in normal distribution, right? It's kind of similar to that. You have to convert it to this form. And normally you have to convert to z less than positive form, right? In this case, you want to convert it to x greater than r form. Now, how would you do that? These are discrete variables. Discrete means only integer values are going to be in this particular case. You can think of it like this. You can say, what are the values that you want? You want 2, 3, 4, 5, 6. These are the values that you want the probability for. What do you not want? You don't want 7, 8, 9, 10, and so on. And you don't want 1 either. These are the ones that you do not want. Okay. Now, can we write this somehow in this greater than r form? Let's think about it. One way to think about this would be, how would you classify all of these cases? All cases from 2 onward. How would you write them in greater than form? What would they be? They would be x greater than 1, right? Greater than 1, yeah. All numbers from 2 onward, if you were to write them in greater than form, you would say they are x greater than 1. And that would give you probability of all of these. But you don't want all of these. You only want up to 6. 2, 3, 4, 5, 6. That's all that you want. So you need to get rid of this part from that total. How do you describe this part? The numbers from 7 onward in this form. X greater than 6. So you subtract probability of x greater than 6 from probability of x greater than 1, right? Because greater than 1 means you're adding probabilities for 2, 3, 4, 5, 6, 7, and so on all the way up to infinity. Greater than 6 means all the probabilities from 7 onward. If you subtract this part from the total, you're just left with 2, 4, 5, 2, 3, 4, 5, 6. And that's what you want. So you could calculate this directly as q raised to power 1 minus q raised to power 6, and that's going to give you the result directly. So you won't have to do all of this. You just do this directly if you're able to figure out how to write it in this inequality form. Does that make sense? So what does this become? Q raised to power 1, Q was 0.7, so that's 0.7 minus 0.7 raised to power 6, and that should give you the result. You can see what that turns out to be. 0.58. 0.58 is not enough. You need to write minimum 3 significant figures. 0.5824. So you can write more, but not less than 3 significant figures. 0.5824. Okay, so that's the probability that we were looking for. You could do it either way. You could do it this way as well, or this way. Both of them work. Okay, now then it says find expected value of x. That means mean of x, expected value of x. What's the expected value of x for a geometric progression? It's given in the form for a geometric distribution. It's given in the formula sheet as well. Expected value of x for a geometric distribution is given by 1 over p. So that's going to be 1 over 0.3. And you can see what that is. It's going to be 3.33 something, I think. Yeah, 10 over 3, which is 3.33333. Okay. Yes, Ali, of course, CI will recognize this formula. So again, I keep coming questions like these. I keep getting asked questions like these. That is this method going to be acceptable? Is this method going to be acceptable? Everything that is mathematically correct, as long as you're showing working for that in the exam, is acceptable. It doesn't matter. So even if there's something that's not part of the syllabus explicitly, for example, in paper 3, you could use synthetic division. That's not part of your syllabus, but that is a possible way of dividing. In mechanics, for example, you could use Lami's theorem. That's not part of your syllabus, but it simplifies things. Sometimes you can use that. Anything that's mathematically correct, as long as you're showing working for that, that is acceptable. Just make sure that you show the working. You don't have to state the formula. You can do it directly. So if you want to write it directly like this, that's perfectly okay. You don't necessarily have to write down the formula. Well, that would not make sense, Moza. If you say probability of X less than 7, okay, you're actually right. That would make sense. So you're saying probability of X less than 7 minus probability of X less than 1. Yes, that will also work. But the problem is the formula that we remember is the one that has greater than sign. So that's why we're converting it to that form. Okay. We don't, so I do not recommend that you memorize all the 4 formulas, but if you do, then you could use this as well. This one is the easiest to remember. So just remember this and convert everything to this form. Okay. But yes, if you remember the less than formula as well, you could do it that way as well. That's perfectly okay. In the formula sheet, it says mu equals 1 over p. Mu is the mean, right? Mu is the mean. So mean is the same thing as expected value. So there are different notations that we use for this. Expected value, mean. For mean, you use mu as well. You use x bar as well. It's all the same thing. Okay. All right. 5 friends will each take their advanced driving test tomorrow. Find the probability that at least 3 of them will pass tomorrow. What kind of distribution is this now? At least 3 of them will pass tomorrow. This is the probability that we want to find. This is not geometric anymore. We're not talking about first success. We're talking about number of successes. That at least 3 of them will be successful. Okay. What's n? So this is binomial. The value of n is 5. There are 5 friends. Out of 5, we want at least 3 to be successful. What's the probability of success? They are successful if they pass the test, right? What's the probability of them passing? 0.3. What's the probability of them failing? That's 0.7. All you have to do is find this probability x greater than or equal to 3. At least 3 means 3 or more. So that's x greater than or equal to 3. That's the probability that you're looking for. Now, greater than equal to 3 means you could have x equal to 3, you could have x equal to 4, and you could have x equal to 5. You would find all of these cases and then add them up together. Now remember the formula that you have, it's written in the formula sheet as well, NCR p raised to power r q raised to power n minus r. Although it's written a slightly different from the formula sheet, will I think have something like this, nr and then p raised to power r and 1 minus p raised to power n minus r. That's the same thing. 1 minus p is q, nr is basically ncr. So that's the formula that's given. Just apply that here. 5c3 into 0.3 raised to power 3 into 0.7 raised to power 2 plus 5c4 into 0.3 raised to power 4 into 0.7 raised to power 1. Plus 5c5 into 0.3 raised to power 5 into 0.7 raised to power 0. Now, I would recommend that you evaluate each one of them separately, putting them all in the calculator directly. That is generally prone to errors. Right. Calculate each one of them individually, and generally in the marking schemes, they write them separately as well. So in case your final answer turns out to be incorrect for some reason, you would get more partial marks if you write it down in steps first of all. Okay, so you do that, and then you add them up together and see what the final result turns out to be. Can somebody tell me what this is? What's the final result that you get from this? When you put this in your calculator, make sure to use brackets around these. Otherwise, calculator will either give you a wrong result or give you an error for some reason. Use brackets around these. 0.163. Okay, so that is what we're getting. Can somebody confirm this as well? Okay, 0.163, that's the final answer that we get. Okay, let's move on. Okay, we still have one part of it left. 75 people will take their advanced driving test next week. Use an approximation to find the probability that more than 20 of them will pass next week. Now, what kind of distribution is this? 75 people will take their advanced test next week. This is, again, a binomial distribution. And then we have to do normal approximation of that, right? So it's binomial to normal approximation. So original distribution is binomial. We have to convert it to normal. For binomial, we know that n is 75 and probability of success is 0.3. Probability of failure is 0.7. The probability that we're looking for is that more than 20 of them will pass. So x greater than 20, that's the probability that we want to find out. Let's convert it to normal first. How do you do that? Mean equals n times p. That gives you 75 into 0.3. You can see what that turns out to be. And then standard deviation is npq square root. That's 75 into 0.3 into 0.7, and then square root of that whole thing. What's the standard deviation? And the mean? What are the values of the standard deviation and the mean? Okay, so 22.5, that's the mean. And then standard deviation, 75 into 0.3 into 0.7. That's 15.75, and square root of that, I'm going to leave it like this so that we use exact values later. Square root of 15.75. Okay, these are the mean and standard deviation. Now we need to find x greater than 20. We have to use continuity correction for this. Greater than 20 means you think of 19, 20, 21. Which one of them are included? Which ones are not? 19 is not included, 20 is not included, 21 is included. So where the decision is changing between them, you have the cutoff and you say it's x greater than 20.5. Okay, that's what you have to calculate now. Now you apply simple normal distribution. You've got everything that you need. You convert it to z first of all, so it becomes z greater than 20.5 minus the mean, which is 22.5. divided by the standard deviation with the square root of 15.75. You can see what this turns out to be. That's probability of z greater than 2.5 divided by under root of 15.75. That's minus 0.6299. Z values in the table are to 3 decimal places, so you would say this rounds off to 630. Now you need to find this from the table. For using the table, you need z less than positive form. This is z greater than a negative value. So you think of, you're getting something different? Can somebody confirm this? Are you getting the same thing? Okay, I'm sorry. I think I did 2.5 there. Yeah, maybe you're right. 15.75. Yeah, you're right about that. I wrote 2.5 in the numerator. That's minus 0.50395, and that rounds off to 504. Yeah, thank you for that. This is the z value that we get. Yeah. Now, we have to convert it to standard form. What's the normal distribution curve? It looks like this. You have 0 in the middle. Negative value is going to be on the left side. So the area that you are looking for is this area. Now we can't find this from the table. It's area to the right of a negative value. However, what we can do is we can just flip this. When we flip this, we get the standard form directly. So this area is the same as the area to the left of 0.504. Using the symmetry of the curve, we can say that area is the same as this area. So this can also be written as probability of z less than 0.504. Now, this is something that you can find from the table directly. Go to the table, see the probability value corresponding to 0.504. This is the table, 0.504. We have 0.5 here, and then 0 here. That's one number that you have to take. 0.6915, and then 504. That's 14, add 14 at the end, and that's going to give you 0.6929. Okay, let's use that here, 0.6929, and that is the probability that we were looking for. Make sense? 0.6929. Any questions on this? No? Is Mustafa still here? Okay, let's look at the last question now, and then we end. Okay, now we have question number 6. Jay and his wife Kaz are having a party. Now he has invited 5 friends, and each friend will bring his wife. Okay. Now, at the beginning of the party, the 12 people will stand in a line for a photograph. How many different arrangements are there of the 12 people if he stands next to her wife and each friend stands next to his own wife? Okay, so the couples are standing together. Okay, so let's do that at the end quickly. Okay, how many arrangements are there if 12 people, of the 12 people, if he stands next to his wife and each friend stands next to his own wife? So the couples have to be together. Okay, we have 12 people in total. What we can do is we can merge each pair of 2 boxes to get 6 boxes in total. So in each box, we would have a couple. Right? So we have 6 boxes in total. In each box, we have a couple. In how many ways can we arrange these 6 boxes? 6 factorial ways. In each box, there's a couple. For example, in the first one, you have J and his wife, K. They can switch places with each other as well. And that's the same thing that happens with each of the other couples. They can switch their places. So we have to multiply it by 2 factorial because of that. And that's going to give us the result 6 factorial into 2 factorial. That's 1440. Okay, that's the first part. Quite straightforward. Okay, I'm sorry about that. I missed this. 2 factorial for 1. What about the others? We also have to do that. Into 2 factorial, into 2 factorial, into 2 factorial, into 2 factorial. How many couples do we have in total? What do we call them? Let's say C1, C2, or let's not call them anything. We have 2 factorial here, 2 factorial here, 2 factorial here, 2 factorial here. You have to do that for all of them, right? Because each of those couples can switch places. So that's 1, 2, 3, 4, 5, another 2 factorial. Or you could say 2 raised to power 6, right? And that will give you the result. Can somebody tell me what this number is? Six factorial into 2 raised to power 6, 2 raised to power 6 is 64. 64 into 6 factorial. That's 46080. That's the result that we get from this. 46080. That's the final answer. Okay, now it says how many different arrangements are there for the 12 people if J and Kaz occupy the 2 middle positions in the line with the 5 friends on one side and the wives of the friends on the other side. And we don't know which side the friends are going to be and which side their wives are going to be on. Okay, now let's think about this. So again, we have 12 places in total, right? And now what happens is, this couple, the hosts, they occupy the places in the middle. So that means if we have these places in the middle, they occupy these 2 places. Let's actually put them in one single box here. And it's a fixed box, it's not moving. Okay, it's a fixed box. In this box, we have that host couple, J and K. Now, in how many ways can we arrange these 2 people? 2 factorial, right? They can just switch places with each other. Now, on one side, we are going to have the 5 friends. On the other side, we're going to have the 5 wives. Let's say we have the 5 friends on the left side. Let's suppose F1, F2, F3, F4, F5. In how many ways can we arrange these 5 people? In 5 factorial ways. Wives are on the other side. Let's say W1, W2, W3, W4, W5. In how many ways can we arrange those wives? 5 factorial ways. But then it's also possible that wives are on the left side and the friends are on the right side. So we consider that case as well. So there are 2 ways of basically moving around this outer box. It can go here or it can go here. So we multiply the whole thing by 2 factorial or just 2 because of that as well, because it's possible that friends are on the left side. The wives are on the left side and the friends are on the right side. The husbands are on the right side. That's also possible. So what we get from this is 2 factorial into 5 factorial into 5 factorial for the friends and their wife. And then we have the middle 2 factorial for the host couple. And that's going to give you the result. 5 factorial is 120. 120 into 120 into 4. That's 57600. That's the result that we get from this. Okay. That was part 2. Let's look at the next one, part B. It says, for a competition during the party, the 12 people are divided at random. Now they're divided. They're not being arranged. They're divided. Divided means they are basically grouped. So this is going to be combination. Keep that in mind. They're divided at random into a group of 5. So group also gives you a hint that it's combination. The order does not matter. A group of 4 and a group of uh, 3. Okay. Find the probability then that J and K's are in the same group as each other. That's a 5-mark question. We need to find the probability that they're in the same group. Now, how many total possible groups are there, first of all, without any conditions? How many total possible groups are there if there were no conditions? Can we find that? The people are divided into a group of 5, 4, and 3. Total possible groups. One group has to be a group of 5, the other a group of 4, then a group of 3. You could choose a group of 5 first. So you would say 12C5. 5 people are put in one group. And then once they have been placed in a group, how many people are we left with? 7. So that's out of those 7 people. Now we have to choose a group of 4. That's 7C4. And once you have chosen these 2 groups, the third group is kind of already chosen now. The remaining 3 people, they're going to be in the third group. If you want, you can write it as 3C3. And that's going to give you the total number of possible combinations. Make sense? You could do it the other way around as well. You could say 12C4, as in you could choose a group of 3 first, and then a group of 5, and then a group of 4. Any order, it doesn't matter. It's going to give the same result either way. Okay, whichever group you choose first, it does not matter. What do we get from this? 12C5 into 7C4 into 3C3. What's this number? 27720. These are the total possible groups that we have. Now, what's the probability that J and K's are in the same group as each other? Now, we are not given which of the 3 groups they're going to be in, right? They could be in the group of 3, they could be in the group of 4, they could be in the group of 5. So we have to consider all of those different cases. So one possibility is that they are in the group of 5. If they're in the group of 5, think about it. So let me actually write it like this. This is a group of 5, then you have a group of 4, then you have a group of 3. You have 3 cases. One case that the couple is in this group. Second case, the couple is in this group. And third case, the couple is in this group. Right? These are the 3 cases that we've got. If the couple is in the group of 5, now they are already there, right? So there's no there's nothing that we have to choose for that couple now. We have already placed them in the group of 5. That's what the first case is saying. What about the rest of the people now? We have 10 people left. Those 10 people left have to be placed in these 3 groups now. In the first group, we had 5 people in total. We needed 5 people in total. 2 of them are already selected. How many more people do we need for that? 3. So out of 10, we select 3 and put them in this first group. And then out of the remaining 7, we choose 4 and we put them in the second group. And then we have 3 people left. That's 3C3. Okay. Then you have the second case when that couple is in the group of 4. In how many ways can we select this now? Out of the remaining 10 people, we have to place 5 in this first group. And then out of the remaining 5 people after that, we need 2 more people for the second group. So that's 5C2. And then the remaining 3 people, they're going to be in the third group. And the last case, out of the remaining 10 people, we need 5 in this group. That's 10C5. And 4 in this group. Out of the remaining 5, that's 5C4. And then 1 person is left. That's going to go in the third group. 1C1, sorry. calculate each of these cases and see what that gives you. What do we get from this? Each of these cases. Total for all is 80, and you're saying individually they are 4,200, 2,520. Please do this calculation separately first. That will save you from careless errors. And then add them up together at the end. 7,980. And now you can find the probability. These are the favorable outcomes. These are the total number of possible outcomes. What's the probability then? 7,980 divided by 27720. And that should give you the correct result. Let's see what that turns out to be. 7,980 divided by 27720. That's 19/66. That's what we're getting. That's our final answer. Is that okay? No problems? Okay, that was the last question. Now, Sufyan is asking about question number 1, part A. Let me quickly have a look at that. And then we end. Let's see how long that is. Okay, so only 3 marks. Becky sometimes works in an office and sometimes works at home. The random variable x denotes the number of days that she works at home in any given week. It's given that probability of x equals x is given by this, where k is a constant and x is equal to 1, 2, 3, 4 only. So basically, this random variable can take values 1, 2, 3, 4. We need to draw up a probability distribution table for x, giving the probabilities as numerical fractions. Now, how can you do that? Probability distribution table, we have some values of x. What values of x are possible? They have told that it could be 1, 2, 3, or 4. And then you have probability of x here. Now they're asking to give probabilities as numerical fractions. That means they should not be in terms of k. Okay. All right. Now, first of all, let's write them in terms of k and see what that they turn out to be. If x was equal to 1, what do we get when x equals 1? K into 1 into 2. That's 2 times k. When you input x equals 1, it becomes 2 times k. Okay. Then you input x equals 2. X equals 2 is going to give you 6 times k. And then x equals 3. That's 3 into 4, 12 times k. And then x equals 4. 4 into 5, that's 20 times k. Right? These are the probabilities that you're going to get for each of these cases. They want to give they want you to give the probabilities as numerical fractions. That means they should not be in terms of k. Can we find the value of k? These are probabilities. The total probability is supposed to be 1. So their sum is supposed to be equal to 1. 32 and 40. So it becomes 40k equal to 1. The value of k turns out to be 1 over 40. So now you can write down these probabilities as fractions. 2 into 1 over 40. What's that? This is right as, do they want simplified form? They don't. So we could just say 2 over 40, and then 6 over 40, and then 12 over 40, and then 20 over 40. And that's what we get. Okay. These are the probabilities. Second part is expected value of x, variance of x. You just have to apply formulas for that and you get the result. Okay, so I hope that was helpful. Now our next class is on June 2023 papers. Whichever of them has the lowest threshold, that is what we will be doing in our next session. Okay. Now it could be on Saturday as well. We might have an extra session on Saturday, but I will confirm if you have that. You would have to do that one paper before that class. Okay, I'll tell you which paper to do, and I'll also confirm if you can have a class on Saturday. If not Saturday, then it will be on Tuesday. Or yeah, Sunday is also not possible. Or I might try Sunday as well. Yeah, so keep in mind, we might have another class on either Saturday or Sunday. If not, it will be on Tuesday. But in any case, the next paper is going to be one of the papers from June 2023 session, whichever has the lowest threshold. Okay, I'll see you again in the next session then. Allah Hafiz. Ali, are you still there? Yeah, so basically I told you, oh yeah, so I please leave me a message on the WhatsApp group. I have another class starting right now. After I get done with that, I will share that video in the WhatsApp group. Please leave a message there. Okay, all right. Allah Hafiz.